Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about a calorimetry problem where you have a reaction going on and they want you to find the enthalpy of the reaction per mole of the substance formed. So let's get into this. So when a 1.0 liter of a 2.00 molar solution of sodium sulfate at 30.0 degrees Celsius is added to a 2.00 liter 2 liters of 0.750 molar barium nitrate solution at 30 degrees Celsius in a calorimeter. A white solid barium sulfate forms. The temperature of the mixture increases to 42 degrees Celsius. And we're asked to assume that the specific heat capacity of the solution is 6.37 joules per gram per degree Celsius, and that the density of the final solution is 2.00 grams per liter. And they want us to calculate the enthalpy change per mole of the barium sulfate formed. Okay, so a lot going on here. So the first thing we want to do is write down the balanced equation. So we got sodium sulfate reacting with barium nitrate. So sodium sulfate, Na2SO4 aqueous plus, and then we have the the barium nitrate. So we got barium nitrate, BaNO32 aqueous, and that's going to form, as they said, barium sulfate as a solid, because the barium, the two inside ions are going to go together. This is a +2 charge on it. Sulfate has a -2 charge. So that's going to be BaSO4 solid. And then the other possible product is the two outside ions coming together. So sodium and nitrates. So sodium has a +1, nitrate has a -1. So that's going to be NaNO3, and that's going to be aqueous because nitrates are all soluble. And so now we just need to balance the equation. So I have two sodiums over here. I only have one over here, so I'm going to need a 2 coefficient. And I have barium. I have one barium, so that's balanced. I have one sulfate, that's balanced. And I have two nitrates, and I have 2 times 1 is 2, so 2 nitrates. So now we have a balanced equation. The next thing we want to do is write down the starting information that we're given before everything reacts. So we're told that for the sodium sulfate, we have 1.0 liters, and this is going to be 2.00 molar, and the temperature is 30.0 degrees Celsius. And then for the barium nitrate, we have it's 2.00 liters. It's the molarity is 0.750 molar, and it's also at 30 degrees Celsius. Okay. So now the first thing we need to do is, because notice they're giving us molarities and liters, volumes of both reactants. So they're giving us an amount of both reactants, and we don't know which one is the limiting reagent. So in this case, we have to figure out which one's the limiting reagent so that we can figure out how many moles of the barium sulfate is actually formed during the reaction. Because remember, they're asking us to find the enthalpy change per mole of the barium sulfate formed. So we got to do our stoichiometry to find the moles of the barium sulfate that's formed. Okay, so first we'll start with the sodium sulfate. So we want to convert sodium sulfate to moles of the barium sulfate. So they're giving us 1 liter, so we'll start with 1.0 liters of the sodium sulfate solution. Put that over 1. And we can use the molarity here as a conversion factor. This means that 2 moles of the sodium sulfate per 1 liter of the solution. So I can put 1 liter of the Na2SO4 solution on the bottom to cancel out with here. And then I'm going to put the moles, that's 2.00 moles, 2.00 moles of the sodium sulfate. So now liters of the sodium sulfate solution cancel out. Now I have moles of sodium sulfate. Now I can use the mole ratio of 1 to 1 to convert from moles of the sodium sulfate to moles of barium sulfate. So let's do that. So 1 mole of sodium sulfate on the bottom and 1 mole of the barium sulfate on top. So moles of the sodium sulfate cancel out. And now I have moles of barium sulfate. So now I can calculate the moles of barium sulfate formed from this amount of the sodium sulfate, 1 liter of the given sodium sulfate solution. And so when I calculate this out, I get 2 moles. Of course, it's 2 moles. 1, I forgot everything's 1. So 1 divided by 1 multiplied by 1, so it's 2 moles. 2 moles of barium sulfate. Okay, then I do the same thing with the barium nitrate. So I have 2.00 liters, so 2.00 liters of BaSO4. And again, this is solution over 1. And now I can use the molarity of the barium sulfate solution, which is 0.750. So that's going to be 1 liter of the barium nitrate. I knew something's wrong. So barium nitrate is what I'm talking about. Na2SO4. And then that's going to be Na2SO4. And then I'm going to have 0.750 moles of the barium nitrate on top. So now the liters of the barium nitrate solution, this is solution, that is going to cancel out. Now I have moles. Now I can use the mole ratio again. So between barium nitrate, so it's 1 to 1 again. So I'm going to use the mole ratio. So 1 mole of the barium nitrate on the bottom, 1 mole of the barium sulfate on top. So moles of barium nitrate cancels out. Now I have moles of barium sulfate again. So I do the calculation. This time I have 2 times 0.750 multiplied by 1 divided by 1. So it's just 2 times 0.75. So that's going to be 1.5. So that's going to be equal to 1.50 moles of barium sulfate. Okay, so now that I've calculated the amounts of barium sulfate that would come from each of the reactant by itself, assuming that it reacts to completion for both, I notice that this amount of the sodium sulfate is going to produce this amount of barium sulfate, but this amount of the barium nitrate that's given to me will only produce maximum of 1.50. So once I produce 1.50 moles of the barium sulfate, I am not going to have any more barium nitrate left over, so the reaction is done. So barium nitrate is the limiting reagent, so Lr, barium nitrate, limiting reagent. So this is the maximum number of moles of product I can form. Okay, now that I know that, I can use this to help me figure out the enthalpy change per mole. Okay, now that that's done, the next thing is to do the calorimetry problem. So let's just remind ourselves. Remember, if you have calorimetry, you are mixing two things together and there's going to be heat transfer. There's going to be heat produced from one thing or released by one thing and absorbed by another thing. So for example, you put a hot metal into a calorimeter with cooler water. The hot metal is going to transfer energy to the cooler water. Water is going to absorb the energy. Metal is going to give the energy to the water. In this reaction, or in this problem here, we have a reaction that's taking place in the solution. So in this case, the reaction is going to release energy and the solution is going to gain energy, right? So the solution is going to absorb energy, the reaction is going to release. And we see that why? Because the final temperature, we're told, is 42.0 degrees. That's a temperature increase, which means energy was released to the solution from the reaction. Okay, so why is that important? Well, because if we take Q, right, or we could do little q, a lot of times we do small q. So Q of one thing, like say metal, is going to be equal, let's say this is the Q that's released, the heat that's released is going to be equal to the heat absorbed. We're assuming that no heat is lost, but there's going to be a negative here, right? So Q1 could represent the amount of heat that's absorbed from the other object, right? So if this was water, then water would absorb, Q1 would be the heat absorbed by the water, and the negative Q2 would be the heat released by the metal that's put into the water, the hot metal that's put in the water. So the Q's have to be equal to each other, right? But opposite, because one is losing heat, the other is gaining heat. And you can rearrange this. You could keep it like this if you want, but you could also rearrange it. I like to rearrange it where you put 1 on one side. So if I subtract both sides by Q1, right? Or in this case, rather than subtract, let's subtract Q2. So if I have negative Q2, I can add Q2 to both sides. I can add Q2 to this side. And then my equation becomes 0 is equal to Q1 plus Q2, right? So you can use this form or you can use this form, right? It doesn't matter which form you use, as long as if you use this form, one side has to be negative, right? So it doesn't matter which side. Technically, the side that's losing the heat, the side that's releasing heat, you would put the negative sign there. But if you forget and put it on the other side, mathematically, it's not going to hurt the problem. Okay, so let's get rid of this since I don't need this anymore. So the next thing we want to do is set up the calorimeter problem. So if we use this one here, so 0 is equal to Q1 plus Q2. Well, what is Q1 and Q2? Well, we have the solution that's absorbing heat, it's gaining heat. This temperature is 42 degrees. And we have the reaction going on. So the reaction is going to release heat. That's the enthalpy of the reaction. That's the heat that's being released. So the enthalpy is going to be the reaction, and the solution is going to be absorbing that energy, and therefore goes up in temperature. So this reminds us that the other equation that we got to use is Q, the amount of heat, is equal to the mass of the substance multiplied by the specific heat multiplied by the change in temperature. And remember, change in temperature is always equal to the final temperature minus the initial temperature. So we're going to use these equations here. You can substitute this in for this, or you could calculate this on its own and then plug it in, right? It's up to you. But I'm going to substitute, and I'll show you in a moment. So now, Q1, if I make Q1 is equal to, say, the heat of the reaction, that's going to be delta H of the reaction. That's the enthalpy of the reaction, the heat giving off, right? The total amount of heat given off in the reaction. So we're going to make that equal to Q1. Well, what's Q2? That's the solution. So the solution there, Q2, is going to be equal to, well, what's the equation? We're going to use this equation here. So here it's going to be the mass of the solution. I'm going to put S for solution. Give me a moment. Yep. And then I'm going to put the specific heat of the solution multiplied by delta T of the solution. So now that I have Q1 equal to this, Q2 equal to this, now I can substitute these in for the Q1, Q2 here. So let's do that. So I have 0 is equal to Q1, which is going to be delta H of the reaction, plus, and then Q2 is equal to this. I'm going to just put in this for Q2, plus the mass of the solution multiplied by the specific heat of the solution multiplied by delta T of the solution. But instead of delta T, I'm going to put in TF minus TI, final temperature minus initial temperature. So final temperature minus the initial temperature. Okay, so here's my equation. Now all I need to do is plug in everything and solve for the missing part. In this case, we're going to solve for the enthalpy of the reaction. So what's the mass of the solution? Well, we don't know the mass of the solution, but we can calculate it. We need to know the volume of the solution. Well, what's the volume of the solution? It's the two volumes added together. You got to remember that. So we have 1 liter, I have it here, 1 liter of this added to 2 liters of this is going to give us 3 liters total. So I have 3 liters, 3.0 liters total of the solution. And they gave us the density of the solution. Where's the density? Right here. So we know the solution is 2.00 grams per milliliter. So I have to convert to milliliters, and then I can use the density as a conversion factor to convert to grams, right? So then that'll give me the mass of the solution. So then I'm going to multiply. I'm going to convert liters to milliliters. So 1 liter goes on the bottom, or I can put 1/1000th of a liter because I know 1 milliliter is equal to 1/1000th of the liter, or 10 to the negative 3. But you could also use 1 liter is equal to 1,000 milliliters, same ratio. So I have 1 liter on the bottom, and I have 1,000 milliliters on top. So liters cancels out. This is solution. Now that I have milliliters of solution, I can use the density here to convert to grams of solution. So I know that's 2.00 grams per 1 milliliter. So I'm going to put 1 milliliter of solution on the bottom, and I'm going to put 2.00 grams. Let me make that grams better. Grams of solution on top. So milliliters are going to cancel out. Now that I have grams, I have the mass of the solution. So now I can multiply 3 times 1,000 times 2. So 3 times 2 is 6 times 1,000 is going to be 6,000. So that's going to be equal to 6,000 grams of solution. So that's going to be the mass of the solution. So now that I got that, I'm going to plug that in. So 0 equals the change in enthalpy of the reaction. That's what we got to find. Plus 6,000 grams multiplied by the specific heat. They gave us the specific heat, which is 6.37 joules per gram degree Celsius. So we'll multiply that. We'll plug that in. So 6.37 joules per gram degree Celsius. And then we have final temperature minus the initial. The final temperature is 42.0 degrees Celsius. So we'll put that in. Let me make sure I have enough room. Yeah. So that's going to be final, 42.0. So 42.0 degrees Celsius minus what? Both of the solutions, when we mix together, right? We're going to mix them together at the very beginning before anything reacts. The temperature is 30 degrees because both of them mix together 30 degrees. So that's going to be minus 30 degrees Celsius. So now I have everything plugged in. I have one equation, one unknown. So now I just solve for this. So when I factor this out, so I subtract this, I multiply this by each other. So then when I get that, I'm going to get, where is it? 0 is equal to delta H of the reaction plus 458,640. 458,640. Right? And then watch here. So we have grams cancel out. The degrees Celsius are going to cancel out here. And then we are left with joules. So this is going to be joules. So now all I need to do is subtract this from both sides. So minus 458,640. So 458,640 joules. And then minus 458,640 joules. And so I got the delta H of the reaction is equal to a negative 458,640 joules. Okay, great. So a couple of things I want to mention here about this. One, it's negative, which means that heat was released from the reaction. So delta H of the reaction, the enthalpy of the reaction, is negative, and that means that heat was evolved or released, and so this is an exothermic reaction. This is what we would have expected because the temperature increased in the solution. The solution absorbed energy. Where did that energy come from? It came from the reaction. The reaction lost the energy. So that's the first thing. The second thing is this is just the enthalpy of the reaction. It is not the enthalpy of the reaction per mole. So, oops. Sorry about that. As I was saying, this is just the enthalpy of the reaction. It is easy to just stop here and say, I'm done, but you're not done because you got to pay attention. They're asking for the enthalpy change per mole of the substance formed. So we got one less step. We got one last step here. So remember, what did I say before? The amount of this that was formed was 1.5 moles. Let me just double check, make sure. Yeah. So remember, I forgot to, I erased it, but remember we formed, so 1.50 moles of the barium sulfate was formed, right? That's what we calculated earlier when we did the limiting reagent problem, right? So now all we need to do is take this amount here divided by 1.5 moles, then we get our answer. So we get, so the delta H, so we'll take negative, so the delta H of the reaction per mole, right, per mole is going to be equal to negative 458,640 joules. Oops. Let me, let me erase this so I can have space. So we don't need that anymore. So now I can do delta H of the reaction per mole, right, is going to be equal to negative 458,640 joules divided by the number of moles of barium sulfate that was formed. And that's going to be 1.50 moles. And so when we calculate that, we get let's see, 306, I'm rounding a little bit, 306,000 joules. Remember, this is in joules, and normally your delta H of reaction is going to be in kilojoules, so we can convert this to kilojoules. So then we can take the 306,000 joules, and 1 kilojoule is 1,000 joules. So we set up our conversion. So 1,000 joules on the top, on the bottom, 1 kilojoule on top. Oh, and this is negative, by the way. Forgot the negative. This is negative. So then joules cancels out. We're going to divide by 1,000, and that means that finally our answer is 306 kilojoules of energy. Let's put per mole. Kilojoules per mole. And that, ladies and gentlemen, is how you do this sort of calorimetry problem. So I know this is a long way to do the problem, but if this helped you in any way, if you enjoyed this video, if you found this helpful, then please, by all means, like the video, share the video, hit that like button somewhere over here, over here. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with, or a topic you need to solve, or a topic you want me to go over, please let me know. I would love to do that for you. Thanks for joining me, and have a great day.